Good morning, everyone. I don't know, it sounds good? Yeah. Okay, so hi, I'm Pablo Manglano, and we are from the University of Alcalá. And we are going to present our research, which is called Spatio-Temporal AI Modeling Urban for Traffic Calibration, a SUMO-Based approach. Well, we are a little chair from the University of Alcalá, as we say as before. He's Álvaro Palicio García, he's my professor. And together with Miguel Ángel López Carmona, we did the research. We are chair center in AI modeling, simulation, and optimization. So as this research, we'll see now. Well, with this presentation, the main objectives were how to develop an AI-based spatio-temporal calibration, how to use digital twin scenarios for this simulation, how to achieve accurate OD predictions and calibrations in short term and also long term or mid term, and how to do incremental fine-tuning on live detectors. So, a little background of this calibration history will be they started with analytical models, but they were not good enough, so they went together to simulation-based models, dimensionality reduction techniques, and then machine learning, which has a little bit of cons, like it requires a lot of label data, and then deep learning, which will be the model we will be exploring right now during this research. So, what's our approach? In our approach, we want to use SUMO for digital twin creation to produce datasets for AI training. So, we generate a complex deep learning engine for accurate spatio-temporal calibration. We use a sliding time window for training and forecasting the calibration. And we achieve a great prediction accuracy with real-time performance. Also, we had to face some problems like data sparsity from some detectors, because the net is not always perfect. We have a lot of detectors, but not all traffic is recorded by these cameras. Also, the graph size, we model a medium city, so not all TADs, traffic area analysis zones, are together. So we had to take this into account to know the data that will be recorded. Also, the trade-off of the window horizon, because we are using a sliding window, so we need to focus on a small value, but big enough to have data enough for the prediction. The model complexity, as we had a lot of layers in our AI model, we had to find the balance between complexity and performance, so we couldn't be able to make the calibration in real time. And also the inline adaptation. That will be a fine-tuning during real time in order to achieve the best accuracy for the model. So this is our methodology. It's a typical AI methodology, so it will have two phases, the training phase and validation phase. In case some of you are wondering, here in this green block is the SUMO, it's our microscopic traffic simulator. And during this research, we will focus mainly in the demand generator and in the calibration predictor. So, with our training scenarios, we fed that into our demand generator, which reassembles a real curve demand. Then the simulation goes into the microscopic traffic simulator, in this case SUMO, and we obtain all the data we want to train the model. So, during the training phase, it will mainly be traffic sensor data and the flows routing. We will be fed into the calibration predictor all the information. And as a main difference during the validation phase, there are two main differences. The first is that the demand is not known during the training, so it's new information it has to predict. And the second one is that we make a validation which we train only with traffic sensor data, and the flows routing is used for validation. So that way we can know if our prediction was accurate or not. Then, as I said before, during our dataset generation of synthetic data, we start with OD matrix from the net. Then we apply a random multiplier, so we don't have always the same demand. We distribute the vehicle fleet and assign random departures time for each vehicle. We extract sinks and sources from our TAD data, and in sub-hourly demand, in this case it is minutely, during a whole day simulation, it generates the trip list and exports it to an OD matrix file. Then all this information from the simulation we talked before is fed into the A calibration predictor, which is a snapshot list, one hot encoded, that holds all the information of the simulation and each time snapshot. So this goes through a lot of layers. In this case, it starts with a graphic attention network convolutional, which is from Torch, and performs the spatial techniques and extracts all the spatial information, which is fed into the stack time and flatten, which prepares all the information for the LSTM layer, which will extract all the temporal features. Then the reconstruct nodal will perform the spatial prediction, and then the edge MLP will predict the time each vehicle will go from one zone to another. In this case, as I said, we're using a medium city. In this case, it's Guadalajara, which is almost 100,000 inhabitants. And we use it because it's a really good strategic important position in Spain, as it is between Madrid and Barcelona, and it will resemble a good scenario for our simulation. So we model the different traffic analysis zones. In this case, it's because of utility. It's a utility model, so we have different tasks. In this case, the color ones and the circles. The circles will be entry and exit points for the city. So it has a little difference because it has the entry exit points do not have inner traffic. So vehicles cannot go in between these tasks. They can only go to another task or exit. So this will be the physical view of the scenario, and this will be the logical view of the scenario. That will be how our AI model sees the net. So, as I explained before, the blue dots will be the color ones from the simulation, will be the colors, and the red dots will be the red circles from the entry-exit points of the city. So as we can see, the inner traffic is only in the blue dots, and this is how our net will be able to predict the spatial prediction. So as I said in the last part, the historical demand profiles, we got 4 different curves. This, as we can observe, they are really different, and we perform 3 variations to each one to have a more detailed scenario and train our model with different data. So I will go to this back later, but with our model training, it was really important because, as I said, we have 12 scenarios from 4 different curves and 3 variations to each one. We achieve some more data, and the traffic detectors, that will be the only information our model gets for the training. But for the validation, we have a model that we know all the vehicles and the traffic and the time snapshot, they go to another zone, so we can make the validation accurate. And then with all this data that is performed in 24-hour simulations, we obtain almost 16,000 time snapshots, and over 120 training epochs, our model has an early stopping method because it's not improving its performance. So it stops, and we know it's correctly trained. We do only have to train once the model for each scenario. So if we, for example, we are training on Guadalajara in this case, we will only have to perform this step once because it's really time consuming. So we want to reutilize this as much as we could. But in case we want to go to another city, there will be no problem, but it will be advised to train this model for each city and its scenarios. So we know how, and this is we know why, and this is how we will make our prediction. So we are using a time sliding windows. So we start with simulation at 0. We will start here with no information at all. Then our first sliding window will capture the first traffic and will perform the next sliding window prediction. This way we use all the data from before to make the next predictions. This way we can really forecast the traffic, because other way we will be guessing what's happening. Here we have feedback, real-time feedback, and even almost in this case during this research, it's every 5 epochs. we make online fine-tuning, so our model gets even better results. So it's trained on this specific day with also the previous training. So that's how, and this is how it looks, or how it is. So here we have a real time where the red line is the real traffic, and the blue dots, the blue line, is our prediction. So what we really perform during this research, what we get, is the calibrated OD matrix. In this case, it's traffic from Centro Comercial to ZB. So we guess this value that will be D for each time snapshot. So for example, in time 60, we guess this value and also all the rest. So we have the time snapshot for the traffic from each time snapshot. That's what we really do. Here we have a more detailed view of the last picture. So we can see the model almost reassembles perfectly the traffic from the validation day, which is not fed into the training, so the model doesn't know this traffic, and it reassembles almost perfectly. Here is a little trade-off, but it almost follows perfectly the curves. So here we have maybe a more mathematical view of the performance of our model. So we can see that the relative error is really low. It's sometimes 0, and in blue we can see when our model underestimates the real value of the vehicles that will go from one zone to another, and in warm colors we can see whether it overestimates the number of vehicles that will go. Here we have some metric results, so it has a very good results. It captures all the relationships, as we can see here. What our perfect value will be 1, but it's really near, and really low errors. So zooming out, we get here the same pattern, the same graph as before, but for each task. Here we predict the inbound and outbound traffic that will go to a zone. So as we can see, as similar as before, we get really good results. This is we made a lot of simulations, and the results were always very similar. So we can conclude that our model performs a good calibration, an accurate one. And here is the same, but accumulated for all the network. So in this case, the variation between training days and validation days can be almost 80% of the traffic. So here is not 80, so we can conclude that our model is capturing some of the complex relationships between the traffic, and is using the sliding windows correctly, as it captures the curves. So this is really good, because there was before some question about this. So our model scalability, we made some math, and we conclude that it is achievable for almost every computer. In this case, this research was done on a home computer, so it's not really complex for a computer. It performs almost 400,000 edge operations, but during the costly part of this research was during the simulations in SUMO, and also the training for the AI model. But fine-tuning and real-time prediction is really fast, as it can be done in almost 3 minutes. So, as a conclusion of the research, we can say that we get accurate flow predictions. Here are the metrics, as I explained before. We are able to make scalable online adaptations, because our model with its sliding window approach can be redone every time, so it can predict the next, and also make fine-tuning, so to improve its performance. This is an end-to-end integration with SUMO, because we start with the simulation from the traffic. We use all the traffic interface to obtain all this data pre-processed to train our model, and then the validation is done again with SUMO. So we use it a lot. And as a practical impact, we've seen in Guadalajara network that we are able to, with its digital twin, to obtain real-time predictions can be used for traffic management in the future. So it's a possible solution for this type of problems. In future works, we would like to make an optimal detector placement, because right now detector placement is quite a big problem or challenge at least, because we train our model with what the cameras see, what the detectors see. In case the detectors do not see some traffic, the model will have to guess or will have to make another. So detector placement is a key part of the research. In this case, we make it optimal hand by hand. So it's not, but we would like to perform a more advanced method for this. We would like to scale to metropolitan cities. For example, Berlin will be great to model. Also Madrid or some big cities, because right now we are with a small city like Guadalajara, 100,000 inhabitants, it's not that much, but we would love to go to bigger cities. And also we would like to implement real-time policy evaluation. For example, last year we talked about dynamic low emission zones, so this will be a great addition to our last research. So we will be focusing on that on the future works. And thank you very much. Hope you enjoyed. Here are our LinkedIn, so in case you want to connect or know a little more, you can. And thank you very much.